right, good afternoon. We are on the clock, 3 o'clock. Some more people will join. Please have a seat. So, my name is Frederick. I usually go by Fred, and I'm here with my friend and colleague, Olivier. Olivier Pellerin, Frederick Detienne. So the Fred is me, Olivier is there. We're both from Belgium. We have been working for a long time for the Cisco TAC. Olivier is still in TAC, where he's principal engineer. And for myself, I have been moved to our engineering team to continue the development of a tool that we call RADKit, which we will also cover in this presentation for the automation part. But I have been a long time TAC engineer as well, and this is where my heart is. I like to troubleshoot problems. All right, so quick question. Who's heard about RADKit already here? Quite many of you. All right. Have some of you started using it? Not that many of you, so we're going to have to change that. Okay, so today is mostly about troubleshooting this platform that was called ASR 1K and that has been removed in Catalyst 8K because, you know, it's easier, not. But anyway, it's the same architecture. So ISR, ASR, Cat 8K, SD-WAN Edge, aka C Edge, they all share the same architecture. So there is only Olivier and I, so you can ask questions on the WebEx, but unfortunately we will not be able to take these questions until after the presentation, so this is when we will answer. In between, during the presentation, if you have any question, raise your arm. We will repeat the question and try to answer. If it takes too much time, we'll simply ask you to take the question offline. So we're going to have a look at the hardware architecture, because on that we will map the software architecture, and that will allow us to explain how to troubleshoot these platforms, especially from a data plane standpoint, because this is really where they shine. Everybody knows how to troubleshoot their BGP. There are dedicated sessions to that. Troubleshoot their IGP. There are dedicated sessions for that. But when it comes to generic platform level troubleshooting and some monitoring, which we will cover as well, we need to understand the architecture. So we'll be looking at the data plane, the forwarding plane, the control plane, and all these pieces. Great. So let's have a look at the software architecture first. So like I said, all these platforms inherit from the ASR 1000 series. It's a very old platform, still works today, but it's slowly reaching end of life, replaced by everything else, like notably the Catalyst 8000, which is our flagship. So there are 3 parts in the hardware that may or may not be visible. I mean, there may be a physical representation of that, like a root processor and some line cards. Sometimes everything is clubbed into one chassis with the ports and the CPU soldered on the same board, like a pizza box style. So there's plenty of form factors, but there is always a root processor where a very important process runs. It's called IOSD. And IOSD, this is why we call it iOS XE, right? That's the operating system that, you know, that's the naming we use for that platform. This is the CLI that you are familiar with. Show IP route, show version, show running config, etc., etc. So all of these commands, they are from IOSD. But where in the past IOSD was the operating system of the box, now iOS is only an operating system, part of the operating system of the device, and all of that runs across other processes. So this OS has been virtualized and placed into a process, and it runs along other processes such as the SD-WAN daemon, OMPD, ConfD, etc. Many of them we don't really care. They are for the TAC. By the way, we will focus the troubleshooting today on what's useful to you. We can go into lots of details about these other processes, but quite frankly, they are not documented. There are very few tools for you to play with. It's kind of a waste of time in a big session like this. So we'll be focusing on stuff that is actionable by you, for you on a day-to-day basis. But these are tools that the TAC will use as well. There are other systems that we use for troubleshooting in TAC, but they're really not usable by the general public, almost not without a developer. Anyway, there is what we call a forwarding manager, and that's another kind of control plane. So FMAN, the forwarding manager, is the piece of software that is responsible for programming the forwarding engine. All right, and then we have a forwarding engine, so to speak, that we call the QFP. Historically, that used to be a dedicated chipset. Today, it's implemented with off-the-shelf silicon, like Intel CPUs, ARM CPUs, etc. But that used actually to be a Cisco silicon chip. You find the crypto assistance there, etc. So, like I said, on iOS, you have all that CLI you're familiar with, show IP route, show version, etc. Then you have other commands like show SD1, for instance, something. Once you type this command, iOS will actually go fetch the data into the SD1 process and display that for you. So it's iOS taking the command, but it's actually going to this other process to ask the question. Then when you have a command that starts with show platform software, again, you type that command on the iOS process itself, so you have only one CLI to deal with. You may see that the tag, they enter subshells and they connect to other components of the chassis. But as far as you're concerned, most of it, and even for us, we start from the iOS CLI. You type the command over there, but the data, show platform software, IPsec, QFP, active, whatnot, this is actually data taken from the FMAN, for the forwarding manager. And then we have show platform hardware commands, and again, typed at the iOS level, but we fetch the data at the QFP level, at the forwarding level. And actually, I'm very glad we don't use really a QFP anymore, because it was quantum flow processor, and it has nothing to do with quantum physics. It has nothing to do with quantum crypto or anything like that. I don't know whether the marketing names come from the company we acquired, I think. So, but anyway, bottom line, these are usually the forwarding statistics. How many packets we dropped, how many packets we forwarded, how many packets we encrypted. So these are really the real-time traffic information and how the data structures are ready to process your packet, like the NAT table as they are in the forwarding engine. We do not troubleshoot the lower layer, which is the SIP layer here. The SIP layer, historically, is the place where we attach the port adapters and the interface adapters. There is nothing to troubleshoot there. We hardly ever have any problem with this. When we have one, again, we contact engineering. But that's even from a tax standpoint, right, where we process hundreds of thousands of cases each year. This hardly ever happens. I think we have 1 or 2 persons who are very familiar with that, because we do not need to troubleshoot that. This is a driver level, and we hardly see anything. If you hit a problem there, you're very unlucky. I'm sure some of you have been. It's a big room. All right. So let's have a look at the forwarding plane. Now, what happens to a packet when it traverses a Catalyst 8500? So you have the input hardware and the packet processing engine core. So when we say PPE, which is part of the former QFP, we have what we call the packet processing engine, and it's made of multiple cores. This is really the most important part. So you have the port adapters, like gigabit interfaces and stuff like that, where the traffic enters. Very low level, that's the SIP level that I was mentioning earlier. The packet comes in, it's really electrical level, right? Few volts up or down. We have bits and bytes, and we put that into memory, and then we feed these packets to the packet processing engine. QoS is also executed in the packet processing engine in these cores, but we have a dedicated core for that. It's called the QoS execution core, the BQS. All right? So QoS for queuing and scheduling. So what happens to a packet? The packet enters, like I said, converted from an electrical signal or an optical signal into bits and bytes in memory. We select one of the PPEs, so we select one of the cores, over which there may be threads, there may be sub-implementation, but it's a detail. And this is where the packet processing really begins. So we will pick, based on the input interface, something that we call an FIA. This FIA is actually a data structure that contains a list of actions that the interface has to apply on each packet as they enter the interface. And of course, it depends on the type of packet and on the configuration. If you have cross-connect configured, we take a certain type of actions. If you have IPv6 configured and not IPv4, but an IPv4 packet enters, we kind of drop the packet, or vice versa. So depending on the full config and the type of packet, we select one of what we call the vectors. And the vectors are simply a list of pointers. So if you are familiar with programming, it's just a bunch of pointers that point to functions. And these functions, in sequence, they will process the packet and apply the feature for which they were made. And this is where you find things like net flow, access list, quality of service, all the stuff that is here on the screen. So every feature in iOS XE is executed in sequence depending on the vector list that is on that data structure. And then the last feature of that input FIA, so FIA stands for Feature Invocation Array. So that's the big name. Like I said, it's a vector. It's a vector of pointers. The last action of this FIA is a routing decision, a forwarding decision. It could be a route lookup, all right? And then we choose an output interface and a next hop, and we proceed with the packet. If it were a multicast packet, we may decide to duplicate the packet and then put it out on multiple interfaces. If it's a cross-connect, then we decide to bridge the packet, encapsulate and bridge the packet, and so on and so on. So in my example here, it's a routing example. It's IPv4 packet. So we take an output interface and a next hop, and we give the packet to the output feature invocation array. So we choose the output interface that also contains a bunch of feature invocation arrays. And these feature invocation arrays are also specific to the type of packet and the config of the interface. So depending on the feature you configured over there, output ACL, output quality of service, policing, MAC accounting, whatnot, then we apply the features in sequence to the packet until we're done processing with the packet. So here, I mentioned quality of service. I wrote it. Quality of service classification and marking takes place here. So if you rewrite the TOS field, for instance, if you decide to classify a certain type of traffic and say, hey, this is HTTP, or this is high priority traffic, this is low priority, this is high latency, low latency, etc., this is where you do the classification. But we do not delay the packets here. We go as fast as we can and try to get out of the processing engine. And it is only at the end, when we're done with all the intelligent feature, that we go into a very dumb feature, but that has to go extremely fast. It's called queuing and scheduling. So based on the QoS classification, we attach a data structure to the packet. We don't modify the packet, but we attach a data structure to the packet, pass that to the PPE 7 in this case, so the BQS. And this core is responsible for storing the packet into a queue and scheduling the output of these packets. So it will just take like a bunch of packets, like millions of them if necessary, manage hundreds of thousands of queues without a problem, and decide whose turn it is to reach the output interface. All right, so classification is done in the intelligent section here in the FIA, and only when all the classification is done, then we give to quality of service for actual queuing and scheduling. So this is very important because it gives us the information about when things get applied. We will go through an access list first, input and output access list, and if the packet survives the access list, then we will decide to queue the packet, which makes a lot of sense if you think about it. But we will also encrypt the packet in the PPE core before we give it to the scheduler. And in the scheduler, the packet may get too late. This is the kind of thing that may happen. So you may see invalid SP, you may see like, how is it called again? Duplicate packet on the remote peer or packet too late, stuff like that. This could happen because of that. So we encrypt first, we do everything crypto, and then we put the packet out for queuing and scheduling. So the good thing compared to the old iOS, for those who are still familiar with that, is that we know exactly in which order the packets will be processed. When it is done, we give the packet to the output interface where it's turned into an electrical or optical signal and put out. And so like I said, each platform is different at the hardware level, but we remap the same software architecture on all these hardwares, and they all behave the same. And the cool thing is that the code, the PPE code, and the iOS code is the same. The main difference will be the drivers that actually drive the software, so different crypto engines, different physical interfaces, different operating system level operations, like platform level operation, but the intelligence of the code, NAT will work the same, crypto will work the same, everything will work the same. And we can always fix that. That's a big difference with the catalyst switches. All right, so here we're talking about the router family, not switching. Switching has a different type of chipset. You may have heard the word Doppler, something like that. Completely different architecture. This only applies to the router architecture. Yes?
It's typically the header that will process on the PPE. Where's the payload stored?
So the question is, since it's the header, where's the payload stored? So in the entire architecture, the packet is in a buffer, header and payload. Everything is like one buffer. We just pass a pointer around, but each element of the PPE has access to the entire packet. So it's not like in some older architecture or extremely fast architecture where the processing engine only has access to the beginning of the header. If you're familiar, the high throughput, high speed systems, they only tend to work on the first few bytes, maybe 100 bytes or something like that of the packet. In this case, iOS, the PPE is able to work across the entire payload. This is why we can have features like firewall, for instance, where we can do deep packet inspection. So the PPE has access to the entire payload. And we don't copy the packet over. We may copy from the hardware to main memory, but once it is there, it's pointer passing. So that's very fast. All right, so what does an FIA look like? It looks like nothing pleasant. That's what it looks like. So you see the output of a command called show platform hardware QFP active interface name IFName gigabit 1. That's a great command. Write it down. I never managed to remember it. Olivier does, I can't. So anyway, this will tell you for gigabit 1 what the feature invocation arrays are, and you will see that there are input invocation arrays, and there are output invocation arrays, and there are layer 2 input, layer 2 output. You see IPv4 input, IPv4 output. You see there are multiple arrays in the feature invocation array table. So when a packet enters, and it is an IPv, so on this example, right, on this router where we took the capture from, when a packet enters an interface, so gigabit 1, and it happens to be an IPv4 packet, we take the one that is circled in blue, the top one, it says IPv4 input. If a packet goes out of that interface, we will take the lower one where it says IPv4 output. All right, and we will process the features in sequence. And so there's a bunch of them that you say, what the hell is that, right? When it says output VFR, output inspect, refrag, all right, L2 rewrite. You never configured those features. But there are a bunch of them that say input ACL, all right, input QoS. Yeah, probably these are the only ones. So you see that some of these entries have an M between parentheses. They are mandatory features. They have not been configured by you. They are put in place by our developers, and they are actually here to ensure the sanity of the packet. So we have a bunch of checks at various steps where we verify that the packet has a legit source destination IP address, that it has a legal shape, that everything is in order, that we're ready to process. So all the M-marked features are usually not configured by you. They are mandatory. They are part of the hardcore code. Those that do not have an M, they typically depend on the configuration of your interface. Sir, you had a question?
That was a question.
There was a question.
If we, for example, configure NAT, the NAT mechanism, it will appear here. Yes?
That's exactly right. I'll repeat that out loud for everybody. So if we configure NAT, then we can expect to see something that says NAT into that list, and that's exactly correct. We don't have documentation for that. That's a very low-level troubleshooting tool, so you have to trust your intuition. Usually, it's very readable, or it's not. If you don't know what it means, you probably don't need it. Right? If it doesn't mean anything to you, you probably don't need it. If you reach that point, you'll call the TAC most of the time, and we may know, or we may again have to call a developer or go to the source code to figure out what it does. But quite frankly, if it's unreadable, the TAC knows, and we don't have to worry about it. If you know what it means, then it is what it means. So that's great. Sometimes life is not too hard. So where were we? Let's continue. So there is also something really interesting here is the show drop. So I told you that the PPE takes care of the entire processing of the packets. It also keeps statistics, and that's something really nice. we keep statistics about all the packets that the system forwards or drops. So if a packet reaches the system, we take a routing decision, a drop decision, or a punt decision. Punt means that we say, hey, this packet is actually for the router itself. Let's say it's an EIGRP hello, it's an OSPF update, or something like that. So we decide, oh, this is not a forwarding plane packet anymore. It's a packet that I should give to iOS to update the OSPF table and then ultimately the routing table, so we would punt it. But we may have to drop the packet. And so we keep a drop code with that, and we say, hey, you know, we received so many packets that we had to drop because TTL exceeded, because IPsec input or IPsec output, like we were unable to decrypt or encrypt for whatever reason, right? And so you see how many packets and how many octets are being dropped, and you have also per interface statistics. So that's a very useful command. It's called show drop. In very old platform, it used to be called show platform hardware QFP active statistic drop detail, because, right? So show drop is very nice. We will see how to use that. Okay, so now, how do we debug that? Because that's why we're here. So the cool thing with the FIA is that we worked with our developer to add a certain feature which we call the packet tracer. And this is how it works. So once again, a packet enters. I am assuming an IPv4 packet. Who's on IPv6 only here? Who has switched to their enterprise network to only IPv6? I have a colleague who's an IPv6 fan, and he would be very disappointed. Come on, nobody IPv6? All right, everybody IPv4? Who's IPv4 only? Okay, everybody. It's a lot easier to type. We make less mistakes. Anyway, so the first thing that happens with what we call the FIA debugger, the feature invocation array debugger, or the packet tracer, is that we create a condition, and we tell the system, hey, when you receive a packet on that interface, and it has those characteristics, for instance, source IP address is this, destination IP address is that, it's TCP or ICMP or UDP with these port numbers, so you just describe the packet at high level. You're not limited to IP. You can match on MPLS labels and stuff like that, but here we're going to work on IP addresses. So you tell the system, when you see a packet like that, I am interested into the details of the processing. So if the packet matches, we will, iOS XE, right? The PPE will allocate a buffer where it will start storing information about the processing of that specific packet. So once you activate the trace, so we will first set the condition in place, and then we activate the trace, and as soon as the trace is activated, we create these buffers, and along the processing of the packet, each FIA entry, each feature entry will be logged into the packet buffer in input and the routing decision, and then in output. All right, so we store all that information. And we do that for a limited number of packets, 1,000, 2,000, 200, no matter how many you need. Well, within memory constraints. But fortunately, this feature is extremely powerful, and you usually don't need to capture a lot of traffic. So that tool is not like a packet capture. There are sessions that will discuss packet capture and all of that, like essentially TCP dump-like or Wireshark-like captures. This actually captures not what enters or leaves an interface. It will capture the information as the packet traverses the system. That's very powerful. I'll show you why. So super useful. When it's done, well, we can view the statistics. When we have captured as many packets maximum that was specified, so let's say we wanted to capture 100 packets, once 100 packets have been captured, the system stops capturing. So if it is a very high-speed stream, you could be working like at gigabit per second or 10 gigabit per second and tell the system capture 100 packets. The packets will be captured in a split second. But then it will stop capturing. So the impact on the CPU will be nothing. If the packets arrive at a very low pace, then it will take more time to capture, but because it's a low pace, nothing will get overwhelmed. The classification is extremely fast anyway, so also you will notice nothing. So this feature is made to be used in a working environment. You can activate the trace, forget you even activated the trace, and it will stay there for weeks or months, customers call sometime, we start troubleshooting, and we see that a capture had been activated in the past. We don't know when, but it doesn't cause any problem. So it is really made to work in production. So we guarantee that. If there is a bug because of that, we'll fix it as well, but we will feel very sorry as well. So anyway, it's meant for production. So it's not the kind of thing that will destabilize your system, which is good. Now, I talked about the easy case, IPv4, input interface, some features, output interface, easy peasy. And now what if we have overlays? Like, what if we need to encapsulate or decapsulate? So let's say we receive a GRE packet or an IPsec packet, right? So something like that. What really do we see? The condition match. So let's say we match on the overlay header, right? So we have the transport header, so GRE packet going from a certain source to a certain destination. The destination is the target router itself. But after GRE decapsulation, we see the overlay packet, the packet that was encapsulated. So if we create a condition on GRE, on the GRE source destination, we will see the packet as it enters the input interface. If we create a condition that matches the overlay addresses, the tunnel packet, so the GRE or IPsec packet enters, but we only look at the outer header. And so we do not know yet that it is a packet of interest. And it's only after IPsec or GRE decapsulation that we can see, oh, this packet was actually for us. We only see it at this stage here when the condition match here. So initially the condition doesn't match because you say, I want to see the packet that go from 10.0.0.1 to 10.0.0.1, for instance, right? But what really enters is a packet going from 200.0.0.1 to 200.1.0.1, right? So you don't see the 10.0.0.1 to 10.0.1.1. You only see it after IPsec or GRE decapsulation. So in the packet trace you will see, the packet will only appear as if it's coming out of the tunnel interface, not from the input physical interface. So that's number one. And of course, as the packet exits the physical interface, you will see the packet going out. In the reverse direction, we would see the packet entering from 10.0.11 into the gigabit output interface. It will match, so we will trace it. We will output the packet to tunnel interface. We will still see the packet, and because we have marked the packet as a packet of interest, we will see the encapsulation into the tunnel. And I'll show you an example of that live. So that takes us to this.
Fred, you are supposed to go on vacation, right?
Yes, I am on vacation.
So we have a problem. So we get our network has been growing over the years, and between those two devices, we are experiencing a slow performance. We have no idea why. I think last documentation we wrote 20 years ago, and the last guy that was managing the network just left.
Thank you.
So I'm thinking I will cancel your vacation.
So we've been doing this presentation for 7 years now, and every time he's got the same problem. Every time.
You shouldn't go on vacation.
All right.
So
let's
you have an hour.
Thank you very much, Olivier. I really appreciate that. Okay, so what can we do about this? Here we are. So this is a nasty problem, right? We have a network, no documentation, or there is documentation, but it's pretty poor. So we have packet drops. It's a needle in the haystack. It could be anything, anywhere, and I don't even have like a topology or something like that. Everybody would love to have a topology. Who has a topology up to date? Some of you, that's great. Even the overlays? Less of you. So, awesome. So let's have a look let's see what we can do. Let's see what we can do here. So I'm going to, I will connect to every device one by one, and we will start troubleshooting. And please have a coffee, because it will take until tomorrow. So instead of that, we're going to use a tool called RADKit. So this is the automation part of this presentation. And this is an SDK that we promote everywhere we can. We're betting our automation strategy on that SDK. So it started as an innovation project, I told you probably a few years ago. But now this tool is going into FMC, SD-WAN, so vManage, wireless controller, ICE. So that tool is going to be embedded in as many platforms as we can, including the CX platforms like CSPC and the CX collector. So it's really a very important tool for us. And this is a tool you can use as well, and the best part of it is that it's free. It's included into your service contract. So if you have a CCO account, you can download the tool and play with it. So it's an SDK. The way it works is, Olivier, you're going to have to give me access to that system. So we will show you later. Olivier already gave me access to the system. So the first thing I will do is connect to Olivier's setup, all right? So through the lab, I don't have physical access to the lab. I can't even SSH to the lab. I don't have a VPN there, but I have Ratkit access. So the first thing I'll do is create a service. Actually, let me show you that. And we are going to go to, where is it? Sorry about that. This is the wrong tool. I apologize for that. Don't say, here we are. Give me a second, sorry about that. I prepared the wrong directory. Ah, no, here it is, here it is. Sorry, I had multiple editors open, that's why. And we're going to go for find path. So let me, I'm going to run an automation here, meaning that I will have a system that will connect to all the devices, activate a packet capture, collect the data for a few seconds, and we will see where the packet is going, right? I think this is the first thing we want to know is like isolate the devices where the traffic is going, and so we eliminate the devices where the traffic is not going, and we will see what we discover. So to do that, I'm just going to activate my Ratkit client, copy my script into this, and I will do it in manual mode. I'm not going to just run code blindly, all right? I will show you what the code does. Little by little, so I'm going to use a PowerShell for that. So the first operation I will do is connect to Olivier's service, which is here, and to avoid typos, I will copy paste. So I'm connecting now to Olivier's setup, and he gave me access to his entire network, but he could actually have decided to restrict me to just a couple of devices. But in this case, I'm acting as a consulting engineer or a partner, and I need access. I mean, I need to roam the entire network. I have no choice. But he could have decided to restrict my access to only 1 or 2 devices. So as you see, there's a bunch of them, and I'm going to focus on, I guess, all the routers, right? There are a bunch of Linux, vManage, we don't care about that. I'm going to focus on the router. They're all C edges. So I will simply say this is service.inventory.filter, and I will say device type C edge, like so. All right, devices, we focus on the C edges. So now I'm going to launch my little script here, and I will capture the data into a trace, and then I will, while it launches, I will show you what the code does. So I will say trace packets that go between the source and destination of the stream that is damaged. In this case, 192.168.11.252, all the way to 192.168.16.252. Right? These are the endpoints of the connection that is too slow, where we're dropping packet or losing packets allegedly. So this system now will deploy a packet trace on all the routers, wait for a few seconds, collect the data, and tell me where it has seen the traffic. And you have seen that here, the packet trace has already been deployed. All right, faster than I can talk, the system is deploying. It's really fast. So what happens really behind the scene? Can you read this? Okay, these are the commands that my script will apply. So first, it will clear all platform conditions. So just in case somebody had started a troubleshooting session before, I want to wipe out all the conditions. Then I will tell the system, I want to trace the packet that go for the IPv4 packet that go from a certain source to a certain destination, which are the parameters I pass to the function, and I want both bidirection, meaning I want an input and output on each interface. So I want to see the packets coming in, and I want to see the packets coming out of each interface, all of them, not a specific interface. So as you see, it's a very global function on the system. if you had to take packet traces, you would have to take a packet, like a packet capture, right? You would have to take a packet capture on each interface, maybe capture 10 gigabits of traffic on each interface. You know, it's 10 seconds on each interface. That's going to be 10 gigabit. That's really crazy. I will say I want a copy of the packets, all right? And I want to trace 64 packets. Sorry, I want to trace 128 packets, sorry. And I will allocate buffer for that, the 4096. Just take this number and use it. It's not a big deal. So essentially, I'm telling, trace the packets that go from source to destination, allocate some memory. I want to trace 128 packets. After that, deactivate yourself. Simple as that. Sorry, I want to trace 64 packets, my bad, and I want to capture 128 bytes out of them, my bad. Okay, so where are we with this? Well, the capture is done, all right? So now I have a trace, and for each device, I can see if we have captured any data. And we see that in this case, that device contains nothing. Trace, SD routing 1.data, there is something, print. Well, we see the packet was there because the capture did return something. Now I can go device by device, or I can simply apply the other function of my script, which is called, how is it called again? Get path, all right? So let's run get path, trace, here we are. So, this packet has been seen on 4 devices. So it goes from source to destination, and it went through these 4 steps. So that's very easy. But now I would like to focus on the packet for which I see drop. So what my script does is simply goes through this show platform packet trace summary, and it looks for a trace that says drop instead of forward. And that will hopefully isolate 1 or 2 devices that do not see the packet. It may not be sufficient, but it may work. Oh, we have drop. So SD routing hub east sees the packet, and it says it's dropping. Let's have a look. Service, inventory, SD routing hub east. I will ask for an interactive session. And what you can see is that I have something that looks and smells like an SSH. It's not a real SSH. It's something simulated by Radkit. I didn't have to type any password. Olivier actually authorized me on his system. I am authenticated. I use my CCO account to authenticate. We will show you that in a moment. I just want to go through the troubleshooting first. We'll talk Radkit in a moment. But the idea here is that I am authorized, I have authenticated, and by virtue of that, Olivier's management system, his Radkit management station, we call it a Radkit service, created the SSH session to the device, authenticated, and replicates all of that to a TLS session back to me. And everything that I do is logged on Olivier's system. So anyway, show platform, packet trace, summary, and we can see the same summary that we have captured. Oh, and we see a bunch of drops, including reasons, QoS policy. So let's read this, all right? So we have this packet number 0 was properly forwarded, packet 1 was properly forwarded, but packet 2 was dropped. So let's look at the details of packet 2. So I will say I would like to see packet 2. Hit enter. So what can we see from here? And this is really the power of the packet tracer. We see that the packet was seen for the first time on tunnel 0. So it came in on a physical interface, but the condition didn't match the overlay addresses because the packet that entered had transport addresses. So after tunnel decapsulation, the router said, oh, I can see now your overlay addresses, the one you were looking for. And I can tell you that I tried to route it out virtual access to, which is another tunnel interface, by the way, so it's kind of funny. I know that the packet entered at this point in the system. This is the uptime in nanosecond since the router came online. And the packet stopped, was dropped, or ended up with successful forwarding after so many nanoseconds. All right, so we know by computing the difference between these 2 timestamps, we can measure exactly how much time iOS took to forward the packet. Yes?
You have a summary that puts an input interface and output interface.
Yep.
What about a condition in which we have one input interface and many output interfaces? I mean multicast packets.
You can do that too. I'll show you that.
Multicast packets, you will see an output going to the many interfaces.
Yep. So we don't. So the question is like, what if there is multicast and there is one input interface and multiple output interfaces? I will cover that on a slide after this demo. So good timing. Okay, so, but this is the summary. This is not something we know at the beginning of the trace. At the beginning of the trace, when the packet enters, it is seen for the first time on tunnel 0, and the output interface is not known yet. Of course, the packet enters. We have not done the route lookup yet, so we do not know what the output interface is, but we see that the source and destinations are the ones we asked. It is TCP traffic, port 22. That's a file transfer. We're very happy about that. The destination port is 4,000. Actually, the source port is reversed. Oh, no, this return packet in this case. So the destination port is 4,790. Great. So this is, you can tell this is coming from the SCP server back to the SCP client. That's how we know. This is the kind of guess you can make just by looking at it. Now, we have debug condition input packet. Don't know what it is, we don't care. Destination lookup issue, that's developer feature. ARL sanity, we don't care. Lookup consume, the packet is not for us, so we can ignore that. For us, Martian, the packet has legit source destination IP addresses. So, you know, there's like a whole bunch of things that we don't really care about. But now we reach the IP input lookup process. Essentially, that's where we do the route lookup. So no special features were configured on that interface. No ACL, no nothing. There's no input feature. That's all I can conclude from here, nothing. So here we perform a route lookup, and we see that, you see the output interface was unknown here, and suddenly the output interface is known, because after the route lookup, we know. But we have not given the packet to the output interface yet. There is one more operation, IP input, IP option process. Again, that's a developer stuff for in case the packet has options, like, you know, you want to trace the packet. There's hardly ever any IP options in IPv4, so usually this does nothing. And then we have an input go to output feature. This is where we are at the bottom of the FIA. Remember the big diagram? We're at the bottom of the input FIA, and we're going to give it to the top of the output FIA. And so from here, we start processing the feature in virtual access 2. So VRF refrag, do we need to fragment, defragment, virtual reassembly, stuff like that? Again, we don't really care. L2 rewrite, MAC egress, nobody cares. But there is a feature called quality of service here that says drop packet because the policy called test decided to drop because we exceeded the capacity of that queue. And that's it. This is why we have drops. So this packet got dropped before it even reached the output interface. Drops are immediate. So I told you that the BQS, the PPE, packet processing engine, will not hold the packet. So it will execute, it will mark the packet, it will do classification, stuff like that. If there is a drop, it will also drop right away. Only if the packet has to be queued, it will be sent all the way till the end to the BQS before going out. And so in this case, the packet simply is dropped. Would you like to see a packet being properly forwarded? Yeah, we can do that. Let's have a look at packet 0, for instance. This one also enters on tunnel 0, but outputs on gigabit 1. Okay, very strange. The previous one was output on virtual access 3. So why gigabit 1? Well, again, packet enters tunnel 0, same source destination. Why do we have a different routing decision? Let's analyze. Okay, so again, there is no input feature on tunnel 0, nothing at least of interest. We do a lookup process. We found the output to be virtual access 2, so we're still happy. Go to feature, so we give the packet to the output interface. We apply all the stuff, but this time QoS does not complain. So the packet survives quality of service. You know, some will succeed, some will be dropped because we don't always exceed the capacity. And what do we do? At the end, it says IPv4 tunnel output final, tunnel protection encrypt. Oh, so actually this is the point where we give the packet to crypto. The packet will be encapsulated, all right? And after the encapsulation process, I'm just kind of forwarding. There is a lot of IPsec related stuff. Okay, it says IPsec, IPsec, IPsec. This is because our developers slashed or divided the code into multiple manageable sections for various reasons. We don't have to know why. But at the end of encapsulation, there is a tunnel go to output. And this is where we are going to give the packet to an actual physical interface, and there's a few more processes from here. But once the packet is encapsulated into IPsec, we still have to give it to a physical interface. So we do another lookup, where is this packet going to go? And it goes to Gigabit Ethernet 1, and the packet continues its happy way all the way to the end. All right? And this is what continues. And the interesting part is because the packet succeeded, we have a packet copy in and copy out. So this is the packet when it enters, and below is the packet when it left. So if any translation happened, in this case encryption did happen, the packet will look dramatically different. So you have a clear text packet in and encrypted packet out. You could have network address translation. We may have fiddled with the payload, all right, if firewall is activated, stuff like that. That's what you see. Is it useful? Great. So the good part, again, if we go back to automation, is we could have gone device by device, but the actual execution was very fast, and I would like to show you again the size of the script for that, if I will find my editor, and I will zoom back. You may not be able to read everything, but it's okay for this. So this is the code. The orange stuff is documentation. It's me documenting the code because somebody will ask me the code, and I'll give it to you, so you'll have documentation with it. The non-red stuff, right, this is code. Actually, this is code. This is the code that distributes the packet trace and condition to all the devices. And here, another function, which is called getPath. This is the code that analyzes the show IP, the show platform packet trace summary, and tells you, oh, I have seen drop or forwards, or I have seen drops, or I have seen just forwards, depending on the parameter, on this and that device. So this is very, very simple. So code is very easy to write. It's something you can do in, like, maybe if you're new, it will take you a couple of hours. With a bit of experience, maybe an hour or 20 minutes. And that's the kind of thing that you can do. So for those who are interested, we have a more advanced session tomorrow, or you can go to the booth, or you can try RADKit. We have a lab. But I have here script that actually allow you to upgrade a network, check the versions of your network, stuff like that, pretty easily. I'll give you some more demo if we have time. Yes? Yes, it will be integrated with upcoming platforms, yes. I'll show you that. So the question is, will there be, so in the case of vManage, for instance, will there be a utility inside vManage? Let me first show you the high-level architecture of RADKit. That's where we are now. That's this point of the presentation. And then we will discuss what comes into the various platforms, if that's okay. So back to our slides. Mission accomplished. All right. Let me, yeah, what is RADKit? All right. So what is RADKit? It's an SDK. It's a software development kit. It comes with a CLI. I have used the Python API in this case. So the client, what I call the PowerShell, right, is really technically just a Python shell in which we pre-imported the entire SDK on your behalf. You type RADKit client, the SDK is at your commands, ready to go like a PowerShell. But we also have a CLI for that. So again, if you'd like to see the CLI or try it yourself, if you really are allergic to Python, you can go to the booth or to the lab, or we can try to give you a demo after this. It's a little bit out of scope because it's not automation, so to speak. So what are the benefits? You can automate. You can enable remote troubleshooters. You have security, and I'm going to be very bold on the security claims here. I'll explain why in a moment. And you can simplify. Simplify, you have seen the size of a script. The good thing is, in my script, I could connect to devices on a bunch of devices at the same time. I didn't have to create threads. I didn't have to worry about parallelization. I didn't have to worry about retransmission, about code failure management, like SSH succeeded or SSH failed. You will not see any of that in my code. Why? Because RADKit manages it for you, and it will tell you, hey, I managed to connect to those devices, and I failed to connect to these. And there's no error. Your code is not going to crash. Regardless of the error, RADKit will simply tell you, I failed to connect to this, and I succeeded with that, and here is the result that I have obtained. So that's number one. Parallelization is done by RADKit. How heavy is it? not very heavy. We use a technology called async IO, meaning that we can manage all of that from within a single process. So we consume a single core of an operating system. So if you deploy RATKit on your system, it will not consume, you don't need a monster VM to run that. You need literally the recommended requirements for the operating system. If they say 4 core, like if Windows or Linux distribution says 4 cores, give it 4 cores. How much RAM do you need? We nominally consume half a gigabyte of RAM. So not a half a terabyte, half a gigabyte of RAM, so 500 megabytes, actually less. We recommend you give it about 4 gigabytes to execute, because sometimes there is a big output. How much disk does RATKit consume? About 400 megabytes of disk space, not even a gig, right? Half a gigabyte. What do we recommend? Give it 100 gigabytes, because it will keep logs for you. You will want to have an audit trail of everything that happens, and the logs take space. It's not RATKit, it's the logs that you probably would want. You can disable the logs if you don't like them. Empower, I'll show you that from the graphical interface. We'll delay that. Secure, why is it secure? We guarantee that all the traffic is secure end-to-end between the client and the service, between the API that I have used and the RATKit service. And more importantly, we spend approximately $1 million per year on maintaining the RATKit security. So we control our dependencies, so we depend on open source code. We monitor these dependencies all the way to the end, so the entire bill of material is known, monitored. If there is any CVE, we have a central unit in Cisco that tells, hey, you know what, this code that you depend on, it has a CVE. It's this dramatic, you have 2 hours to respond, or you have 1 day to respond depending on the gravity of the situation. We fix that. If you keep your RATKit up to date, your entire tool chain remains up to date. Of course, you can bring your own modules. You don't have to keep with ours only, but the stuff that you depend on from RATKit is taken care of for you by Cisco. You just need to maintain that. And last piece, if you have noticed, there was not a single password in my scripts. I didn't have to store them into a file. I didn't have to hard code them. I didn't have to type them. And the reason is simply because RATKit, the passwords are stored in a vault, in a RATKit vault, on the RATKit service, which I will show you in a moment. Actually, let's go to the architecture. And the scripts that you use, they are authorized to execute, but they do not need the credentials. The credentials are managed by the RATKit system itself, and we guarantee that they are double encrypted, addressed, et cetera, et cetera. So you don't have to worry in your automations about managing very sensitive data. So this is why I said I would be very bold on security, because it matters a lot. Now we're also going to talk about data privacy. So what's RATKit made of? This is your network. It's the VIP. It needs love. It needs help. So we need a RATKit service there. So that's a process. It can be embedded in Catalyst Center. It will be embedded by Spring into ICE, FMC. By the end of the year, the wireless controller, vManage, and a few other platforms. I think Crosswork is on its way as well. And the CX platform, like CSPC, and the new collector, so the next generation of the CX agent. CSPC already can support RATKit, and the CX agent future will also support RATKit. My team is working on that with the CX agent team. So, but you can run it as a standalone unit, and you have latest and greatest, which is what we recommend today. It's probably the best installation. This RATKit service has an inventory. It knows how to connect to the devices. It has the credentials to do that. A RATKit client is an application that can talk to the RATKit service. The service only manages inventory. The client is able to place queries to the service asking, hey, I'd like a show version on all these devices. And RATKit service will go collect the information and give it back to the client. The client will never open a connection to the devices. If the client and service are co-located, so same network, the client and service can talk to one another. All right, so if you use it for your own needs, client, you will point it to a service by IP address or by FQDN, and the client will open a TCP, actually a TLS connection to the RATKit service. That's it. If you want to give remote access to the TAC or to engineers or to your favorite Cisco partner, if they already use RATKit, you can actually use the RATKit cloud. You don't need to set up a VPN. We take care of that for you. RATKit service and client will open an egress connection to the cloud service. It's an outbound connection, but it's bidirectional. So traffic can flow in both directions. And through that, the client will open a new session. So it's through the cloud, but it's end-to-end encrypted. So the number one question we get is like, how much data do you, Cisco, keep into the cloud? And the answer is 0. We can't. We can't because what we see is encrypted blobs between your support engineer, Cisco, or partner, or whoever, you maybe, right, from home, and your RADKit service. All the data is stuck there. We can't see anything. And if somebody asks, we are not even in a position to decrypt that. So that's a good thing for us and for you. And so at the end, RADKit can speak a bunch of protocols like SSH, REST, OpenAPI, NetConf, Yang, and SNMP v2 for now. We're going to be adding SNMP v3 soon in case you need it. So you can really troubleshoot a lot of stuff. We can export an SSH session like I have shown, as well as web UIs, REST APIs, stuff like that. So it's also possible from RADKit to upload data directly to a service request, meaning that if a TAC engineer says, hey, you know what, I need this core dump, all right? You don't need to download the core dump and then re-upload it. The TAC engineer will say, hey, there's a core dump. Do you mind if I catch a copy of that? And if you say yes, we will trigger the upload directly from RADKit to the case node without other intervention. And it's going to be a background process, so during that time, the TAC engineer can keep troubleshooting, so we don't waste any time. So the good thing now is that the TAC engineer shares their display, and you can do whatever you need to do, what they're doing, work with them, work on your email, respond to the phone, anything you need to do. But we get to work. And the big advantage for you if you go with the tech support like that is that all the cases that we have in this mode, they go to CE pending and hardly not anymore to customer pending. Only if we have a question like, can you show me again how to recreate the problem? Or I think I have found something I need to sync up with you. Yeah, this remains. But for data capture, we're pretty autonomous. So like I said, security, data privacy, I'll let you read the slide. All the data is encrypted, at rest, in transit, end-to-end. So nothing special to say. All the authorization, the list of users, the credentials, they are on-prem on the RADKit service, never uploaded to the cloud. So that's also quite important. Like I said earlier, we have a booth, we have a lab. Go visit them. It's worth trying. Oh, yeah, last thing. And I'm going to address your question here. So going back to the packet tracer. Patterns of interest, multicast replication. So what happens if a packet enters and there are multiple copies of that packet going out? This is what the packet trace will look like. You will have one packet entering. It will say, the source interface will be gig 0, the output will say none, and the status will be cons, for consumed. So it means that the PPE, the packet processing engine, will have consumed the packet, stop it there, and then it will create 3 copies of it, and it will output these copies on gigabit 2, 3, and 4. So that's what you will see in the packet copy. So that's exactly the multicast scenario. Same thing if you have fragmentation. One packet enters, the packet is consumed, and 2 fragments output. So you see the packet entering, being stopped, cut into 2 halves, and each half gets forwarded separately. You see the 2 halves being forwarded.
This output does not differ from this one before.
Correct.
How you must look deeper.
You must look into the detail of the packet to see what happened, yes.
After, when you show this output of this command packet tracer,
Yep.
you have each step for each action. Okay.
Correct.
So what about the situation you have, for example, this fragment situation? So you will have for this one line of command, you will have output only for this 0 packet, and okay, this concentrated and the end of the life of the packet, or we have next information about packet number 1 and next information about packet number 2. How would your look like?
So the question is like, how does it really look like? I don't have a packet fragmented here to show you. Maybe we can try to prepare one after with a large MTU. But the bottom line is that it will look like the other trace. So I'm going to.
What I can do is on the WebEx room, I can put on a.
Yeah, that would be ideal. We'll capture one for you and put it on the WebEx. It will be faster. But essentially, it will look like this trace. So when you do show platform packet trace 1, right, or packet trace 0, you will see that at some point it will say consumed instead of drop. It will say consumed. The packet will end there. And if you look at packet 1 and packet 2, you will see that it's a continuation of the previous packet, like fragment number 1 and fragment number 2.
So where will
I see. To be honest, I don't remember from memory, but like I said, Olivier said, we'll do the test and send it over to you. Yeah.
So yes, I will put it in web, but what you will see is the kind of parent to child relationship. It says my original packet is packet X.
Yes.
And I am copy number 1, I am copy number 2, I'm copy number 2. So you will see that. I will put a few examples in the room. It's easy for me. Yes, absolutely. I will put that.
Yep. All right, so yeah, this is it. And what we have, virtual reassembly. So it's the opposite situation. We may have to reassemble packets before we forward in the case of firewall, and it's pretty much a non-event. That's what you will see here. The big, essentially, it would like the 2 packets are forwarded, like nothing happened, but you will see that one of the packets had a huge delay in consumption. That is the only case the PPE will store the packet. It will store fragment number 1 until it has fragment number 2, verify that both fragments go well together, and then it will forward fragment 1 and 2. So you will not see really something special here. You will only see that one packet had a very long delay. And that's the first fragment waiting for the second fragment. All right, and there are a bunch of use cases. We discussed the tunnel, so yeah, it's rather obvious in general what happens. Okay, so I'm going to fast forward now. In the slides, by the way, there are a bunch of hidden slides that show like a series of scenarios. Just to show that they are covered, they're usually pretty readable. Now I'm going to leave the floor to Olivier, who is going to talk about specifically what we have done in the SD-WAN area.
Absolutely. Thank you, Fred. So you have seen Packet Tracer, which is a per-box tool. We can automate that using RADKit. But in Enterprise, so we have Catalyst Manager, vManage, depending on how you want to call it, that exists, which initially was released for SD-WAN. And nowadays is as well working for what we call SD routing, so which is the router autonomous, but it has a DTLS connection to vManage, so it can be managed and provide statistics. And because we have this controller, we have developed something. You can really call it as a packet trace light, but what we want is to leverage the controller. And the way things are is let's take like the problem that we had before, like. Fred is having an issue with a connection and is calling the help desk. And he asks the help desk, hey, I have a problem to reach Office 365 or God knows what application. And you, as an operator, you are going to connect to vManage, which is your controller. And what you do is you are going to simply say, hey, I would like to trace between that IP and that IP, or from that IP, or I don't know what site. You will put a condition and you will to trace it. And what we do is we are going to do a netconf request coming from vManage to a device and say, please trace on that site for those parameters, simply. And that's the first thing. So we just harm the condition in one place, and then the magic starts to happen. And we get the traffic, so we receive a packet. That packet gets forwarded and traced. And that tracing, we send that via streaming to vManage. Now the packet is going to get forwarded, right? Whenever, and as well we send like generic statistics and a piece of routing information and things like this to vManage. And that packet is now getting forwarded to the tunnel interface, going to the network. And what I'm explaining is valid for SD-WAN, but as well as SD routing. So if you use SD routing and you have DMVPM type of infrastructure, so you use an HRP, that is going to work as well. So you will then encapsulate that traffic, right? So you know that you need to forward. And what we do is simply, you see here that we inserted an NWPI header. That's a SGT tag, so a CMD header, and that has all the information related to the tracing that I'm doing. So we insert that information here, and we forward the packet. It arrives to the hub, for instance. On the hub, what do? We say, oh, I got a packet that I need to trace because there is that header. So now the condition that was set on one box is transitive. We send it through the network. And that's really where the interest is. You don't have to get into a lot of boxes because you don't know where you go. You might have multiple paths. It could be extremely complex. The system is going to append that data into the system. So I know that I need to trace it. So I trace it, and I stream data to vManage. So imagine that your provider is dropping packets. Well, vManage knows now that I encapsulated 100 packets on the first router, but maybe I received 20 or 80 on the second router. So I know that I lost 20 packets in transit. So we can see drops that are local, drops that are happening in the middle, and we have a huge visibility on things. And so on and so on. So the packet gets to the destination router, it gets forwarded, we start to send, we know that we trace it, we start to send telemetry, and then the packet exits the SD routing or SD-WAN network. So that's the power of that solution. So to summarize, the packet without NWPI in case of SD-WAN looks like this, right? IP, UDP, ESP, MPLS, and then the original packet, all that thing gets encrypted. When we turn on NWPI, we just insert that 32-byte header that has all the information that we need. So let's do a demo. That would be more. So should be like this. So Fred was showing you. So I just run a trace in SD routing mode just to show you a few things. So Fred was running that flow before. I did a trace, and what you see is really interesting. So we have a level of detail that is sometimes bigger than what the packet tracer gives us. Like, for instance, I know that the flow was asymmetric, that it came via different type of interfaces, but what I get, and here you see the DMVPN, so I'm in the SD routing world, that I know all the information in an easy way for a human to read that says, hey, I did that lookup, I selected that route. Then I had ECMP, I selected this tunnel. And the path was decided by routing. I send it to DMVPN, and so on. And then he says, hey, I received that traffic coming from the tunnel interface. I took this routing, and the traffic here went to a different tunnel interface. And you can see that information in multiple ways. So that's something that's extremely powerful. I have a second demo that we're going to run from the start. That will be SD-WAN related, where I have like a system where there is a lot of traffic going through. And I'm going to show you the level of detail that we can get. So you see, you get to tools on your vManage. You select network-wide path inside. So obviously, I am in SD routing mode. I go back to SD-WAN. And I'm going to, let me see, this one is stopped. I will run a trace. So what information do I need, regardless of the mode? I need to know the site where the condition is going to be applied the first time. So in case of SD-WAN, I need to select the service VPN and a subnet. So let me be a little shallow, because I don't know exactly what is the address of the client, so I will use a /24. And that's about it. As soon as I click on start, we are going to do that netconf request to the router that is on that site.
Yes. By the way, Olivier, so while the capture is taking place, this is the same feature that we have used from the CLI. So if you have SD-WAN, you have a super fancy graphical interface. If you want to go for a network, the packet condition that we have used, instead of /32s, use /24, or whatever suits you, IPv6 included, MPLS labels, etc. So it's the same feature.
Yes.
And instead of using RATKit to deploy, now you use SD-WAN, which itself will use netconf. That's the key difference.
So you see, so I clicked here on View Insight, and it gives me what match the condition. And what we see is that I'm capturing a bit of NTP traffic, there is a bit of SSL traffic, a bit of DHCP, the flow, and we start to have more and more flows. So we are going to trace up to 128 flows, and then there is some dampening mechanism. It's in the slide, I'm not covering that, but the one that is interesting me is SSH. So I will filter. I'm just interested by the SSH flow. Now the UI return me the one that I'm interested into. So I click on the small plus button, and it gives me some information. So I will have the direction, so upstream, downstream, on one hop, what is the local device, what is the remote device. So here we have something interesting. So on the local edge, so the CH1, we have local drops. So the system is able to tell me, Olivier, we are dropping that flow because of tail drop. But you can even get more information. So if there was one loss, I would have one loss that would be increasing. That's not my case. I have the jitter, I have the delay, the latency, all that information. As well, what is really interesting is I know the QID. So imagine that tomorrow you are configuring QoS, or you are modifying a QoS policy. That tool is going to tell you, looking at the flow, what queue you use. Is the traffic is forwarded, is it dropped, what is the queue size, what is the average queue for that flow. So here you see I have the queue depth. I know the max, where 137 is when we drop because the size is 136, and it takes snapshots on regular basis. And it says, well, in average, you are in the position 66 in that queue line. So you start to have a lot of insights on QoS, for instance. You will have that in many ways, for many features. Like, for instance, if I go down, it will give me a visual representation of what you had in the packet tracer from Fred. But we just stripped out, let's say, the arcane feature, and we just focus on the one that typically matters. So you see that they are all in black, but there is one that is in red. If they are in red, that means that there is something to look at. So let's have a look. So obviously, so here it's difficult with the screen, sorry. But I have an SLA violation. If you do SD1, we have SLAs, and then you steer traffic based on the SLA. And that's what the information tells me. But as well, the tool say, hey, if you want to see the policy that you have, you click on it, you get the information, it's retrieving that from the device, and you can start to analyze a lot of things that are happening, in your network from one location, from one UI. So that's what gives you this tool, so NWPI. And obviously, you have a lot of features. I will just show a last one. There is one called the Insight Summary. What it gives is the type of application that match your condition, what we saw flowing. But what is interesting is going to say, hey, I've seen dropped. Those drops are as well on your Cisco ThousandEyes flows. So in my case, I have ThousandEyes as well integrated in my setup. So sometimes I get the question, Olivier, why NWPI? Why ThousandEyes? Well, those are two different complementary tools. ThousandEyes, those are the probes that give you your network health at any time, but ThousandEyes is not going to tell you that your Q6 is dropping traffic because it doesn't have visibility. Only visibility that you get on the router is that SNMP view to the router, right? And nothing more, nothing less. Here, it's really the magnifying, lens that you put somewhere in your network to find out why we have lower performance, why we have that damaged flow. So you have this type of information. Let me go. Then you have so you can have all the events. It gives you, so my flow it just started. It's going to tell you the number of flows, the drops, when the drops are happening. It's really something that's extremely powerful. Like what your applications, where they are steered across the network. you see them going, this flow is going to get to, this application, sorry, is going to get steered to this TLOC, so to that tunnel interface in case of SD-WAN and things like this. So there's really a comprehensive tool that allows you to trace what is happening. And again, tomorrow, you want to change your application awareness routing policy or any policy, you validate with this. So what are the enhancements that we have put? So 2015, we have SD routing support. 2016, we have packet replay support. So in 2016, obviously 2018, that is going to get out in August, which is a long-lived train. In 2016, I can take a pickup and I can do a replay. So let's imagine that you have so that will work bidirectional on a DIA use case. So if you want to look at a DIA use case, we can do the replay. That's going to work. So I guess for SAS, if you had like a SAS capture and you want to replay it, so for SAS validation, it's going to be extremely useful. So that's one thing. The second thing is it will work as well between edges, but it's unidirectional. But still, you have like a UDP flow. You want to validate how it will behave based on your new policy. You can do it. You don't have to have the flow. So you can run it in a CML or God knows where. So that's where we are. And yeah, related to again, RADKit. So we had that question before. So 2018, RADKit is integrated in vManage.
And so specifically, what will be integrated in vManage, because that was the question. It is the RADKit service that will be there, so you won't need a separate VM, etc. You will be able to activate it. It's all opt-in, by the way, right? Nobody forces you to do that, but of course, it's pleasant for everyone. So RADKit service will be integrated into vManage, activate it at a click, decide which edges and whatever you want to share with your tech engineer, or use it for yourself for your own automations. Okay? In the meantime, you have a standalone implementation, which will do the trick. Yes?
So the question is, does it come with DNA advantage? It's really part of the base package. So
yes.
You get vManage,
yes.
or as a Catalyst, you will have it. It's there. There is no licensing whatsoever.
Yes. So one thing, though, to know about Catalyst Center, the way RADKit was integrated specifically with Catalyst Center is extremely limited. It's only usable by Cisco personnel. I do not know why the business unit decided to do that. It was their choice. In the case of vManage, we're not going to have the restrictions, but in the case of Catalyst Center, you have to have your standalone implementation. Sorry. Yeah, so I mentioned the TAC, but also developers, and I was just discussing with somebody before starting the call here. They're experiencing trouble with their vManage, and the vManage developers have a remote access into that system, and so now our customer has access to the best people in the world to actually isolate the issue and come up with a conclusion without forcing anybody to stay overnight, capturing packet, doing some crazy things. So when you really have a very complex problem, it turns out to be very, very useful. You can invite not just TAC, but also developers, partners, like I said, extremely powerful. Okay, so if we have a few more minutes, I'll give you another demo of RADKit, like a couple more scripts that would trigger maybe your interest or show you how easy it is to use. But before we do that, I'd like to show you one more tool on iOS XE. It is resource monitoring. So you remember in the beginning when I told you iOS XE is made of many components and the iOS is only one process. It looks like the operating system, it has the CLI and all of that, and it is true. But when you look at the memory and CPU consumption with show platform CPU or show platform MEM, you only see the iOS consumption. You do not see the other CPUs. So we have a new command, well, it's not new anymore, but we have this command that very few people know about. It's called show platform resources. And this one, there's normally plenty of commands to go fetch the CPU and CPU, sometimes it's ASIC, right? Essentially, how busy is a processor, how much memory, and what kind of memory we have, DRAM, VRAM, SRAM. There's like tons of different types of RAM with various speeds and everything. And in the past, you were supposed to be an expert in all of this and understand your chassis inside out and query the specific details. With Show Platform Resources, you get a consolidated view of all the resources of the platform, compute and memory and storage, and it will break it down in the various components of the chassis. And because you have no idea, and I have no idea what is B4Q Pool 124, I don't know what that is. It's something that our developer decided was useful. I do not know the difference between DRAM and IRAM. Actually, the difference is speed, and there is less of one than the other, and we use them for different purposes. But who is really concerned with that? Not many people. You just want to know, is my system healthy, right? That's the question. So even if we do not know what these type of RAMs are and which subsystem they belong to, you have for each entry something that says, well, this is the current consumption, and the warning is at 75%, and it's critical at 85, right? That would be for the B4Q PMD at the bottom. But another resource, like the DRAM, for instance, would only become critical at 85%, and warning at 85 and critical at 95. So the table here tells you what the resource utilization really is, and when you should start worrying about that. And we keep that updated for each software version and each hardware platform so that you don't have to go to the documentation. It's very poorly, if ever, documented. It's all internal. So this single command gives you a comprehensive status of the platform. If you monitor your platform, this is the one place to check on iOS XE. Much better than Show Platform Resources, Show Platform CPU, and I just can't explain why we do not recommend it more often, but it's definitely a call to action. And finally, we have a way to troubleshoot, but that's more when you troubleshoot with the TAC. Let's say your QFP, your packet processing engine, becomes a little too busy. We can actually use the packet tracer in a very creative way to actually get a breakdown of the various traffic going through the system, and we would be able to tell you what kind of traffic is actually hogging your packet processing engine. All right, so that's quite useful. The commands are there. You can use it for yourself. It's not too dramatic. It will stop by itself as well, but it may have a little more impact than a packet trace. So use it. Better call the TAC if you're going to use that. But we can give you a breakdown on how the system is utilized. Bottom line, if we want to wrap this up, we know usually people try to troubleshoot through the control plane. We look at the configuration, what could possibly go wrong. That's the first reflex. We check interface statistics. That's useful. You will see plenty of drops. They are consolidated. It's hard to know sometimes where the drops are coming from, or is this drop really affecting the traffic flow that I'm interested in? Well, the packet tracer gives you a perfect view of all of that. Before we end, like I said, I have maybe one thing to show you here. I have another small script the reason I would like to show it to you is to show you how simple it is to code with RADKit with a very basic example. And I have something called show version, all right? And this script here, let me make this bigger, right? Again, a lot of commands. This command will actually go fetch a show version on every device on the network. So let me connect to a RADKit service. Actually, I will use the same as before. So I'm going to take that, add it to my super terminal here. Okay, and we have a bunch of C edges. What are the version of these C edges? Show version C edges. Oops, devices. Here we are. So this will actually connect to each device in parallel and tell you what version is running on each of them. So what if I have a DNA center running on the network and I don't want to query all the devices? Now I'm going to connect service. I'm going to connect to another lab, client.service cxlab Frankfurt, fat fingers, here we are. Service inventory. So this network contains a catalyst center. It is right here. So let me make this a little smaller. Increase the window size. Service inventory, okay, it's not great, but anyway, service inventory DNA center. So there is a DNA center over here, and I can have a show version DNAC in this case. I will show you in a minute what it does. So service, inventory, DNAC. So I'm telling, hey, go fetch the device version, but don't query the devices, query DNA center. I just do that. I have my answer, super fast. And the script is laughably simple as well. Who has a CCIE DevNet here? Nobody? Who scripts using REST API, stuff like that? A few of you. So I think you're going to like this, right? When you authenticate with DNA Center, you have to provide credentials, you get back a bearer token, and you have to redeem the token on each query. And you have to put the right headers, the right cookies, and all of that. So now look at the size of the script here. There is only one command to get the data. The credentials are filled in by RedKit, the bearer token, all the session expiry and everything is taken care of for you by RedKit. So in one command, I fetch one URL, I get all the data in JSON format, display the output, and done. That's how simple that is. So that is why we're promoting that system, because it allows you to automate your network, focus on the problem at hand without the boilerplate code. This would take probably 50 lines or 70 lines of code with all the import, all the management, securing the credentials, yada, yada, yada. And for most of us, our patience or brain power would be exceeded by the boilerplate. Here, you focus exclusively on the data you want to handle, and that's it, all right? It's simplification. So, and the security is native to the system. The passwords never navigate in the system. I would like to thank you very much for your attention. I know it's getting late. Enjoy the rest of Cisco Live.
Thank you.
Thank you, Olivier.